Hello students, so here we start our third unit of the topology, that is compactness and connectedness in topological spaces. So first we start with the compactness, and for this we need a definition of open cover. Let X be topological space, then we take a collections of some open sets of X, then this collection is an open cover for set X if this union of open set covers X, and this union of open sets is also contained in X. So we can say that X is equal to union of these open sets. Then we can say that this collection is an open cover for topological space X. Now we have a definition of compact space. A space is compact if we take any open covering of X and it is a collection of some open sets of X which covers this set X that contains a finite subcollection that also covers X. So it means if we take collections of some open sets of X which covers X, it means X is equal to union of these U alphas, and we take any subcollection of this collection. So let us take B beta. So it is contained in U alpha collection, and if this collection is finite and also covers X, it means X is a union of these B beta, then we can say that X is a compact space. So it means if every open covering of X reduces to a finite subcollection which also covers X, so then X is a compact space. So next we have some examples on the compact spaces. In the first example we have any finite subset of topological space is compact. So in the first, if we take X is a finite set and we take any collections of some open sets of X which covers X, so it means X is equal to union of U alphas. So if X is itself finite, then this collection will also be finite. So we can say that if we take any open cover of X, then it will reduces to the finite subcover of X. So we can say that X is a compact space. And the second example, any subset of indiscrete topological space is compact space. So if we take indiscrete topology, then we know that we take phi and X are only open sets in indiscrete topological space. So if we take any open cover of X, it is X only which covers itself. Now we know that it is a finite set because it contains only one member, that is X only. So this open cover has also reduced to the finite subcover. So we can say that any subset of indiscrete topological space is compact. And third example, if X is any set with A is a subset of X and tau is containing phi X and that subset and its complement, then X is a compact space. Because if we take A and A complement, so both are open sets in X, and then we can write X is equal to A union A complement. So both are open sets and which covers X also, and these are finite because it contains A and A complement. So this open cover of X reduces to a finite subcover because it contains only two members, so it is a finite set. So it is a finite collections of open sets which covers X, so that X is a compact space. Now further we discuss the examples of the non-compact spaces. It means examples of that spaces which are not compact. So first is any infinite discrete topological space is not compact space. So we know that in the discrete topological space, singletons are also open. So if we take any collections of those singletons as open cover, so we take open cover as singletons X, and X belongs to X. As X is an infinite set, so this is an infinite open cover, but it has no finite subcover which covers X. So we can say that infinite discrete topological space is not a compact space, and if it is a finite discrete topological space, then it will be compact space. That we have discussed it earlier, that any finite subset of any topological space is compact. And the second, the set of real numbers with the usual topology is not compact. So if we take set of real numbers and take a usual topology, then it is not compact. Now in the usual topology, open sets are open interval. So we take open sets as in the form of open intervals. So we take a collections which covers X, that is set of real numbers. But this open cover has no finite subcover. Of R. So this set of real numbers with the usual topology is also not compact space. Now further we discuss some results based on the compact spaces. So our first result is, if X is a compact space, then it is a line of space, but converse need not be true. And we are already familiar with the term line of space. That is, if every open cover of X reduces to a countable subcover of X, then that X is a line of space. So if we take X is a compact space, then from the definition of compact, then every open cover of X reduces to a finite subcover of X. So which implies that every open cover of X reduces to a countable subcover of X. So which implies that X is a line of space. But the converse of this result is not true. It means line of space need not be a compact space. So we can prove by taking one example. So let us take counter example. Let us space set of natural number, and we define discrete topology on this. And we know that in the discrete topology, singletons are open. So if we take any collections of open sets in natural number, then we take singleton n, where n is a natural number. So this covers n because it contains all natural number. So this is a open cover for n, and we know that set of natural number is countable. So it is a countable open cover, but not finite. So it is a line of space but not a compact space. So in this result, every closed subspace of compact space is compact. So for the proof, let X is a compact space and we take any subspace of X, that is Y, which is closed subspace. Then we have to prove that Y is a compact space. So we have to prove that every open cover of Y has a finite subcover. So for this, we take open cover of Y. Let us take collections of open sets in Y. So it means Y can be written as a union of these V alphas. Now as Y is a subspace of X, then for each open set in Y, that is V alpha, there exists open set. We take U alpha, which is open set in X, such that V alpha can be written as U alpha intersection with Y. As V alphas are the U alpha intersection with Y, so V alpha is contained in U alphas, and if we take union with alpha belongs to I, then this union also containing union of all U alphas, and this union of V alphas is Y. So here we can say that Y is contained in union of U alphas. So as Y is containing union of U alphas, now further if we take union with Y complement, then we will get Y union with Y complement, which is contained in union of U alphas with Y complement. As Y is a subspace of X, so Y union with Y complement will become X. So it is contained in union of U alphas and union with Y complement. So as Y is closed, it is given, then Y complement is open. So from this collection we can say that Y complement is open and this union of U alphas is also open. So this is a collections of open sets which covers X. So here we get a collection of open sets, that is Y complement and U alphas which covers X. And it is given that X is a compact space. So this open cover reduces to a finite subcover. So we can write X is equal to Y complement union with finite union of U alpha I. So X is equal to Y complement union with finite collections of U alpha is here. Now if we take intersection with Y, X intersection with Y is equal to Y complement union with finite union of u alpha i's intersection with y. So as y is a subspace of x, so x intersection with y will become y only. Now it is y complement intersection with y, union of finite union of u alpha i's intersection with y. As y complement intersection with y is y, so and union with u alpha I intersection with y. So it is finite union of u alpha I intersection with y. As this is the collections of open sets in X, and as y is a subspace of X, so it is finite union of v alpha i's, which is a open sets in y. So open cover of y reduces to a finite subcover of y, so which implies that y is a compact space. Now in this next result we have continuous image of compact space is compact. So for the proof, let two topological spaces x and y in which we take x is a compact space and also we take a function f from x to y, which is a continuous function. Then we need to prove that continuous image of compact space x, which is f of x, and it is a subspace of y, is compact. So to prove that f of x is a compact space, we take open cover for f of x. So we need to prove that that open cover reduces to a finite subcover. So let u alpha be an open cover for f of x, as f of x is a subspace of y. Then for each open set u alpha, there exists an open set v alpha in y such that u alpha can be written as v alpha intersection with f of x. So u alpha is equal to intersection of v alpha and f of x. Now from this intersection we can say that u alpha is contained in v alpha. So if we take union both sides, then it will be union of u alpha is contained in union of v alphas, and u alpha is a collections of open sets in f of x which covers f of x. So it is f of x which is contained in union of v alphas. So it can be written as x is contained in f inverse of union of v alphas. So it is further written as union of f inverse of v alphas. Now x is contained in this union, so as v alpha is open in y, and it is given that f is continuous function, then its inverse image is also open in x. So its inverse image is given by f inverse of v alpha is open in x. So this set is open, so its union is also open. So it is a collections of open sets which covers x. Thus this collection f inverse of v alpha is a collections of open sets which is a open cover of x, and it is given that x is a compact space. So x is a compact space, then this open cover reduces to a finite subcover. Since x is compact, then this open cover finite subcover of x. So x is contained in the finite union of f inverse v alpha is. So it is finite collection here, then it can be written as f inverse of finite union of v alpha i's. So it is further written as f of x is contained in finite union of v alpha i's, and it is a finite collections of open sets in y. So if we take intersection with f of x both sides, then we will get open set collection in f of x. So this intersection is f of x only, and it is contained in finite union of v alpha i's intersection with f of x, and these are u alpha i's which are finite open sets in f of x. So this finite collections of open sets covers f of x also, so which implies that f of x is a compact space. Now in this result we will prove that compactness is a topological property. So for the proof, let two topological spaces x and y in which we take x is a compact space and f is a function from x to y which is homeomorphism, then we need to prove that y is compact space. So for this we take open cover for y. Let v alpha it means we can write it as a union of v alphas, and it is given that f is a homeomorphism, so f is onto as f is on 2, then we can write f inverse of y is equal to f inverse of union of v alphas. So it is x, so x is equal to f inverse of union of all v alphas. So this can be further written as x is equal to, we take union outside and f inverse of v alpha. So v alpha, so it is a collections of open sets in Y as V alpha open in Y, and because of the homeomorphism of F is continuous also. Then its inverse image, that is F inverse of V alpha, is open in X. So it is true for each alpha. Now F inverse of V alphas are open, and it is a collections of open sets in X which covers X. So X is compact, then open cover, that is F inverse of V alpha, reduces to finite subcover. So we can write, so X is equal to finite union of F inverse of V alpha, which can be written as F inverse of finite union of V alpha i's, or which further implies that it is f of x is equal to finite union of V alpha i's, and it is y because of the homeomorphism map. So it is finite union of V alpha i's, and V alpha, it is a collections of open sets in Y which has reduces to a finite subcover of Y, so which implies that Y is a compact space. Now in this lecture we have discussed about the compactness and some properties of compactness in topological spaces. So in the next lecture we will discuss about the connectedness in topological spaces. Thank you.